So the Klein-Gordon equation is not a linear equation, but it is possible to satisfy the special relativistic energy condition with a linear equation, but this can be done in an abstract mathematical space. So let's think about getting there. So what I mean by a linear equation that satisfies this is something like, we ultimately need to get two derivatives in time associated with this, related to two derivatives in space here, right, the del squared plus m squared applied to the function. So we can write minus I d mu. Right, this is going to be something somewhat meaningless, but it's sort of a heuristic to get us to where we want to be. But let's write this. That's a kind of operator. That's an operator. And let's except we have it's actually not a very meaningful, because this has four components, and this is just a scalar. So this is not just one equation, but if we do d upper mu minus m times psi, then this is, let's operate on this with this. So we'll just write this out, go along for the ride, and this becomes I d mu psi minus m psi, which gives us, so now we do this on this, and so we have minus and minus cancel, so we have d mu psi. Then we have this and this, so it's minus I d mu m psi. Of course, m's a constant, so it just comes out, goes along for the ride. Now we're here, minus I m d mu psi, and then we have plus m squared psi, and that's equal to d mu psi. Here, let's pull the m out, and so we have an im here, so we have d mu. If we can consider this to be similar to this, with no additional, that's just a d by dt, given the metric, then this, sorry, did I miss? We want this to cancel. So I should have a plus sign in here. Let me see what happened here. When I do this, minus mi. When I do it on this one, here I have a plus sign. So one of these, the lower one is a plus sign. I think I did that right. So these two can cancel out, and this gives us plus m squared psi. And so we can see that we can build an equation that satisfies the energy condition from breaking up things in this way. But of course, individually, these things are not the same, even if we could consider them separately. So what we really want is to consider the possibility of breaking things up in this way, such that we have two similar things that, when essentially squared, gives us this equation. So this will turn out to be possible, but it's a very abstract kind of thing. We're going to have to bring in other terms here. It will make these things more meaningful, especially individually, so that we'll have linear equations in space and time, and this will bring in things called spinors, because the way to do this is to bring in additional terms here, and these two things will be the same. Essentially, you get a thing that looks the same on both sides. You square it, you get this kind of thing. But what we need are objects here, matrices, 4x4 matrices, which makes these functions have 4 components, right? So we're going to end up with 4x4 matrices, and so these psi functions need to have 4 components. And these are called spinors, and spinors are objects that obey special relativity. They're a certain group in mathematics. So it's a very abstract mathematical space that we're led to. We'll have additional structure. So additional structure associated with these objects that do not exist in the Klein-Gordon equation field. And so we're really talking about the difference between scalar, right? The Klein-Gordon equation represents or describes scalar fields that obey special relativity, and here with this strange abstract mathematical space, we're talking about spinor fields.